for reasons of time and keep you on track. So our pleasure to introduce Daniel Johnson, who's been working on his thesis in creating a new supersonic in-draft tunnel for us. So welcome, Daniel.
Awesome. Thank you guys for being here and taking the time out of your day. And hopefully this project will be interesting. Stephen and Damon, can you guys hear me right now?
Affirmative.
Great, thank you. Okay, so the goal of this thesis is to design and build an apparatus for producing supersonic flows so that we can do aerodynamic testing on campus. Now, right now, the aero department has a supersonic wind tunnel, but that wind tunnel is very old, it's rusting out, it's not sealed very well, and it has a really small test section. The idea is to replace the kind of the more decrepit piece of hardware with a new, better piece of hardware that's more easily instrumented, produces better flows, and will be useful for use in labs, for fluids labs, used by students doing student testing with clubs, and then future master's projects and doing research. The big performance criteria we're looking for with this project is the test duration, so the amount of time that a supersonic flow is able to be produced, the Mach number that's able to be obtained, and then the test section size, which will govern how big of a model that could be tested in the chamber. So really quick, I'm going to go through a brief background of supersonic testing and the ways in which typically people produce supersonic flows so that we can test vehicles that are eventually going to fly at really high speeds. So right before I get into all of that, it's important to note the big driving factors behind doing supersonic testing. So cost, like any project, cost really drives what you're able to do. And that cost for supersonic wind tunnels is broken down into the facility cost, or how much it costs to build and construct it, and the cost to run it. So if you're going to go do a run, how much is it going to cost you to actually perform the test? For the operational cost, it's a good ballpark estimate of how much power is required to run a tunnel is with the jet power of the flow. So if you take the density rho in the test section times the cross-sectional area of the test section times the velocity cubed, that gives you a really good number for how much energy or how much power is required to continuously drive that flow. So as you can see, the higher the velocity is, as you increase velocity, the power required increases drastically, proportional to velocity cubed. So for low-speed wind tunnel testing, power isn't a huge requirement, but the faster you go, it becomes a major deciding factor in what you're able to build and do. So some of the methods that people use to try and reduce that power requirement is by decreasing the cross-sectional area of the test section. So that's just basically reducing the amount of air that you're flowing through, reducing the velocity. So at a particular Mach number, where Mach number is just the ratio between your velocity and the speed of sound in the fluid, given a lower temperature, you're able to hit the same Mach number for a lower velocity. So some tunnels run cold and are able to run for a lower power requirement than other tunnels which run hot at high velocities for a given Mach number. And then test duration. So if you run a tunnel continuously, you have to spend that power the entire time the tunnel is running. But if you run for a short duration, the total energy that's required to perform a test can be much lower. So if you have a high power requirement, but for a very short duration, the energy you spend total is greatly reduced, and you save a lot of money that way. So I'm just going through right now some of the major architectures that are used for supersonic flow testing. So kind of the biggest, best way that people do supersonic testing is with what's called a closed loop or return wind tunnel. Basically, the way this works is you have a very large motor that drives a compressor. And this is like a multi-stage compressor, just like what's in a jet engine. And you raise the pressure in the flow. And when you get that high pressure, it drives through a converging diverging nozzle, which brings the flow up to the Mach number and the test conditions that you need to test at. The flow then passes through a test section, goes through a second throat and a diffuser to bring it back down to a low speed where you don't attenuate large losses, as large of losses as you do at high speed. And the flow returns back around to the inlet of the compressor and goes through again. This is really nice because you can run continuously, but usually they're really large. This is a very simplified diagram of one, but there are a lot of other systems that are also required, including vacuum storage and pressure storage and all these different things. So the cost to build this is immense, and then the cost to run it is even higher. So just to give you a ballpark, so NASA Ames has a pretty famous tunnel called the Unitary Planned Wind Tunnel, and one of the test sections is 9 feet by 9 feet wide, so it's quite large, but to run, it uses the same power requirement as the city of Sunnyvale. So like when they run, they have to like call the power company and say, hey, we're about to increase California's power consumption by like 1%. So it's a huge, huge endeavor to run this, and I believe to be in the tunnel and running, it costs about $10,000 an hour. So even if you decrease the size, those numbers will scale down, but they're still going to be high. It's going to cost a lot to run it, and it's going to cost, and it's very complex to actually build. So this was very briefly considered to be a solution and then immediately thrown out because it's just not really feasible to do it on campus, just for space requirements, money requirements, and complexity requirements. So I mentioned intermittent testing, so just testing for a shorter duration and being able to get a test to attain a test point for just a short amount of time. So the big way that historically and classically people do this is with a blow-down wind tunnel. So it works in the same way as the other tunnel, where you have a high pressure on one side of a nozzle and a lower pressure on the other, which allows you to reach a high, whatever Mach number you need. But in this time, you spend a long time pumping up a large storage tank that's separated from your nozzle by a number of things, but mainly a valve and a pressure regulator. And then you either exhaust the flow out into atmosphere, or you can also exhaust into a dump tank and thus get a bit bigger pressure ratio. But you spend time pumping this up, and then you open the gate valve, and air starts flowing through the pressure regulator, and that regulator keeps the pressure constant throughout the test, even though the pressure in the storage tank is continuously going down. This is the same type of wind tunnel that Cal Poly has on campus, but it runs for just a few seconds, which is long in the realm of high-speed testing, but it also has a really small test section. It's like 4.5 inches by 4.5 inches, which makes it really difficult for a student. Like if a student wants to go and build something to put in there, they need to have a really, really precise, small model. It's difficult to instrument, and it requires just the pressure regulators that are required for high flow rates are non-trivial and pretty difficult to produce. And you need really large enough valves to get a large test section diameter are also difficult to get. So this is a modification to a blow-down wind tunnel, and basically what I've been talking about is you have a high pressure on one side of a nozzle and a low on the other. What's most important to produce a supersonic flow is not the absolute pressure difference between those two sides, it's the pressure ratio, which allows you to get a Mach number. So going from a pressure of 1,000 psi to 10 psi is the same, according to the nozzle, as going from 10 psi to 0.1 psi. It's just the ratio from the beginning to the end. So an in-draft wind tunnel works on that premise, where it's using as its high pressure just the atmosphere, and you evacuate a vacuum chamber and draw air from atmosphere into through a nozzle and through the test section. Benefit of this is you don't need high pressure storage. It's a much simpler system. You don't need a pressure regulator, but there is an added concern of if there's moisture in the air when you accelerate through the nozzle and drop the temperature and pressure really low, that the water can condense out of the air and form a fog. So your test section would just look like there's a cloud going through it. So you can add dryers, and that adds a little complexity. And it's also kind of difficult to have, again, large valves large enough to allow these kinds of flow rates to pass. You also have reduced control over your test condition because you're at the mercy of the atmosphere. It's kind of like whatever pressure and temperature you're at that day, that's your stagnation conditions for your test. Now this is going on the extreme end of intermittent testing. So this is a reflection shock tunnel, and it's used for kind of the highest Mach number and highest velocity tests that people do. And basically the way it works is you have a long tube which is partitioned into a driver section and a driven section. And it's partitioned by what's called a diaphragm. So instead of having a large valve that turns, you'll put a thin diaphragm, which is usually made of like stainless steel or aluminum, and that diaphragm is ruptured. So you have a high pressure in the driver section and a lower pressure in the driven section. And when you rupture that diaphragm, a normal shock wave starts to propagate down through the tunnel. And so in this diagram, this is kind of like in the middle of the test. In section 1, you have all the air that was in the driven section that hasn't seen the shock wave yet. So it's just sitting there, doesn't know what's going to happen yet. Section 2 is air that's moving now down the tunnel, that's moving down the tunnel that has just undergone a shock. Section 3 is the air that's kind of acting like a piston to drive the air in section 2 and that shock wave down the tunnel. And then section 4 is has not yet seen. This is an expansion wave that travels up through the tube. Has not yet seen that. So that normal shock wave propagates down, hits the nozzle inlet, and reflects back. And what it leaves behind is a region of really high pressure, high temperature, stagnant air. And it's kind of like the thrust chamber in a rocket engine, where you have flow or air or a gas at a really low velocity that you then, but high pressure that you then expand through a converging diverging nozzle to achieve a high Mach number. This was strongly considered, but it turned out that the pressures and the temperatures that would be reached to do meaningful testing were really, really high, like on the order of many hundreds to thousands of PSI, and what weren't really going to be feasible for use on campus. And additionally, the hardware that's required to maintain those pressures are also really heavy and also expensive. But this is kind of like used generally for like atmospheric entry and points where like those other wind tunnels just can't reach those high temperatures and Mach numbers. Now this is called a Ludwig tube, and it's kind of like a cross between it's a special type of blowdown wind tunnel. It's kind of like a cross between a shock tunnel and a blowdown wind tunnel. So it's a lot simpler in that it has one long driver tube, which you pressurize, and then a diaphragm partitioning the driver tube from the nozzle, test section, and dump tank. You evacuate the dump tank with a vacuum pump, and you rupture the diaphragm. And when you rupture the diaphragm, you cause expansion waves to go left on the screen. And as the expansion wave passes, it causes all this high pressure stagnant air to start flowing rightward and then go through the nozzle and into the test section. This is actually a really, really, really cool piece of hardware, in that you're able to hit Mach numbers on up to about 4.5, and that's limited by you start making a flow that's so cold that you start to liquefy the air, like not just condense water out of it, but you're actually turning the constituents of air into a liquid from a gas. You can hit temperature or test times on the order of 100 milliseconds, which is pretty good. It sounds short, but with the instrumentation and the videography that we have available to us today, it's plenty long enough to get good tests in. It's cheap to operate. Could be just the power to run a vacuum pump, an air compressor, and whatever diaphragm that you rupture every time. But it can be on the order of a couple dollars per shot. The one thing that was a limit, not usually for most universities, but kind of a limit for us, was in lab space, is the tube for a Ludwig tube was usually around 40 to 60, has a length over diameter ratio of about 40 to 60. So however big the tube is in diameter, it needs to be 40 to 60 times that long, just for a number of reasons. But we didn't have really the lab space to have a meaningfully large test section, meaning bigger than the test section in our current blowdown wind tunnel, in a straight line to line up a tube, a nozzle, a test section, and a dump tank. So this is really close to the best option for what's good for us. We just had a space constraint that we had to deal with. So the design the architecture that I ended up developing is kind of a combination of the Ludwig tube and an in-draft wind tunnel. So basically the idea is to have exactly a Ludwig tube, just without the high pressure tube. So it works like an in-draft wind tunnel in that you're using atmosphere as your high pressure reservoir, and you evacuate a dump tank to be your low pressure reservoir, giving you the pressure ratio that you need to achieve whatever Mach number you desire and whatever Mach number you design the nozzle for. The Ludwig tube is already a very simple device, but it's even simpler than that. And you're able to produce supersonic flows for actually in a really small floor space. So all you need is the dump tank, nozzle, and test section. And then for my specific design, we're actually able to compact it even further. It's different from an in-draft wind tunnel in that there's no valve. You just use a diaphragm instead. So you're able to start the flow much quicker. For a valve to turn and to achieve starting of the nozzle usually takes an appreciable amount of time. But you're able to have a much smaller dump tank by using a diaphragm, which ruptures on the order of milliseconds to maybe 10 or 15 milliseconds, and develop a supersonic flow really quickly, do a short test, and then the chamber fills, and the test is over. So I'll go over my methodology and talk about my system design and how I went about actually solving the problems that arise with trying to accomplish this project. So first, we had a major piece of hardware. I had access to a major piece of hardware, which is a vacuum chamber that Dr. Gregg was able to acquire from Edwards Air Force Base. It's an excellent piece of hardware, but when we got it, it was in a state of disrepair, and it sat outside for a number of years, and all the seals and surfaces had rusted out. But it afforded the opportunity for a decently large dump tank to use if we could get it operational. So it has, on its sides, it has 4 large flanges to allow easy access into the chamber. So that would benefit having vacuum access, attaching the nozzle and flow path, and then also instrumentation access. And then it has a door on one side, which is so you can open and close it to do whatever you want on the inside. It's fairly large, about 120 cubic feet in volume, which is about, on its exterior, it's about 8 feet to each dimension. This is just a quick shot of the chamber after it had been refurbished, after the rust on the flange surfaces had been removed, and then ground and polished, and then new flanges had been sourced to replace them, and new seals were sourced. So we got it working as a vacuum chamber, and that was kind of like the first step that had to be taken in order to use this for the rest of the project. This is just a quick a layout of the final design of the project. So instead of having the diaphragm, nozzle, and test section exterior to the chamber, I actually utilized a window, which is in the side of the chamber, to view the nozzle, and kind of combined all of the inlet flow path geometry with the chamber itself, so that it's all self-contained. So that circle right there is an 8-inch diameter window with which we're able to view the flow. There was a challenge that had to be overcome in making sure the nozzle was able to be located right at that window, but I'll talk about that a little bit more coming up. But basically the idea is that there'd be a diaphragm at the inlet. That diaphragm would be ruptured and allow flow into the chamber, and we can view the flow right at that nozzle exit. So here's a close-up diagram of the actual nozzle design. It consisted of 6 parts: an inlet bell, 2 adapters, which were just basically adapted the rest of the flow geometry to the this large flange, which is a really thick, large aluminum piece that seals off the end of the chamber. Those 2 adapters bolt together with bolts, and then the inlet bell is connected to the adapters, and then the nozzle extension and nozzle connect together using this thing called a V-band, which I forgot to bring. But So the nozzle is fairly large, and that's just the nozzle piece I brought here, so you guys can look at that. I don't think I'll pass it around because it's kind of heavy, but that's it. One important thing in the design of this flow path was making sure that each segment of the nozzle was located concentrically. So for each piece, a shoulder was machined into one side and a counterbore was machined into the other, so that those two would slip into each other and then be located concentrically to make sure that there weren't any forward or rearward facing steps introduced to the flow, because that would potentially cause a flow separation or impact the growth of boundary layers through the tube. So all those ended up, they had fairly tight machining tolerances, but they ended up working out well, and we had one minor issue with it, but it works really well in locating all the pieces and then clamping them together. This is the nozzle that was designed. So in order to perform a project all in a year that has a reasonable scope and is able to demonstrate the viability of this test system architecture, a number of simplifications were made, and one of them was just using a simple conical nozzle. So I designed just a simple conical nozzle to a Mach number of 2.5 with an exit diameter of 7 inches and a 12-degree half-angle expansion. It's sitting right there. It's 15.5 inches long. And the analysis was pretty simple. Like viscous effects weren't taken into account, and the tolerance on the throat diameter and the exit diameter was big enough that an appreciable change in Mach number could be seen. But that was okay, because the main point of this project is to validate the operation of the tunnel, but not necessarily to really precisely hit a particular test point. So this is showing the effective test section for this system. So as the flow goes through the nozzle and it starts expanding through, when it gets to the end of the nozzle, the flow along the edges undergoes what's called a Prandtl-Meyer expansion fan. And this is just basically the flow expands out into the volume of the chamber. But because the flow is moving supersonically, the fact that it's expanding out into the chamber is not communicated instantaneously to the center line of the flow. So the area of incidence, of effect of that expansion is mapped out by what's called a Mach wave angle, which for this Mach number is 23.6 degrees. So this is called, that shape is, it's actually a cone, but it's commonly called a test rhombus. So anything that you put inside that region has a constant Mach number, temperature, and pressure. So you don't need like walls on the side of your test section. This is what's called a free jet test section. And then on the bottom, that's the view of the test rhombus through the window. So everything mapped out in red right there is the effective test section area. So there's the largest diameter of 7 inches, but in the future, larger nozzles, I think I can show that larger nozzles can be used just for shorter test durations and can utilize more of the window space. So initially, did an initial analysis to try and predict the test duration that could be achieved with this type of system. So a number of different nozzle exit diameters were considered over a range of Mach numbers. And basically, if the exit diameter is kept the same, to achieve a different Mach number, you have to change the throat to change the area ratio of the nozzle. I defined the end of a test as when the pressure in the chamber rose to the point of being equal to the exit pressure from the nozzle. And at that point, the flow would go from behaving like an underexpanded rocket nozzle, kind of going through the atmosphere, to being an overexpanded rocket nozzle. So then the pressure would come in and cause shocks at the end of the nozzle and impact the viability of the test condition. Sizing the different nozzles, especially for really large nozzles like the 10 and the 12-inch diameter nozzles, the test duration was pretty short. I ended up selecting a 7-inch diameter nozzle because for a Mach number of 2.5, a theoretical test duration of over 100 milliseconds could be reached, which is on the order of a Ludwig tube, of what can be achieved with a Ludwig tube, while still having a reasonably large Mach number, and has an exit diameter that's slightly smaller than that window, so you can see the edges of the nozzle if someone ever wants to go back and try and characterize the nozzle starting process or anything else with the nozzle. So this is a picture of the entire nozzle assembly. It's kind of distorted because it's end on, but those two fasteners are the V-bands that link it all together. And the whole thing is, I believe, 42 inches long. But because of those V-bands, the whole thing can be quickly and easily assembled and disassembled, which is very important especially for attaching the inlet bell to the inlet adapter, because we put the diaphragm in between those two pieces, and we can get a diaphragm replaced in about, I think, 2 or 3 minutes, so we can turn tests over very quickly. So now I'm going to go over the validation experiment that I used to make sure that the tunnel worked as designed. So this is a view, so I can actually pass that around, but this is a view, this is the test model that was used to try and validate the flow, or to validate operation of the tunnel. And that's a picture of it sitting within the test rhombus of the nozzle mounted in the test section. So here's a diagram just kind of showing the layout of the test and showing each of the components of the nozzle. And the idea is to be able to look through the window at the test rhombus and identify the oblique shock waves generated by that wedge. And since that is a really simple planar wedge of a known angle, for a particular Mach number, there's one solution for the angle of the oblique shock wave of the oblique shocks coming off of the model. So by viewing the test section, if we can see the shock waves and measure their angle, we can calculate the Mach number and show that indeed we have supersonic flow and it's at this particular Mach number. So yes. So this is a schematic showing the optical system that was used in order to image the shock wave. So the shock waves are imperceptible to the human eye typically, but what you can do is if you can produce a collimated beam that goes through the test section, when that beam encounters a shock wave, the shock wave constitutes a very rapid change in density, and light refracts when it goes through a medium of different density. So when the light goes through a shock wave, it bends slightly. So then when you pick up that beam on the other side with the camera, everywhere where there's a shock wave shows up as a line, and you can see it pretty clearly. So to produce that collimated beam, you need a light source, and we pass the light source through a diffuser, which just makes a diffuse wall of light that's easy to send through a pinhole. And the light radiating from that pinhole is radial, so it's radial, going straight from a point source. And it then passes through a plano-convex lens. Unfortunately, when we got to the point of testing, the lenses that we had available, one of them wasn't of the optimal shape, one of them was spherically shaped, which produces a lot of what's called aberration or distortion in the image. The other one was good, but they were a little bit smaller size than would have been optimal, but we were able to still produce a reasonably collimated beam going through the test section out the window, and then through a second focusing lens, which then focused it in the high-speed camera that we borrowed from the mechanical engineering department. So I mentioned that for the shock tubes, or for shock tunnels, typically the diaphragm material would be stainless steel or aluminum or something like that. Because we're only the pressure that has to be contained by the diaphragm is just 1 atmosphere, we're actually able to use a much lighter, simpler diaphragm, which makes bursting the diaphragm much easier and makes worries of the diaphragm going through and damaging test hardware much smaller. So I ended up using cellophane, and the literature seemed to suggest that by using cellophane, the material, when it was ruptured, would shatter, producing a lot of small pieces that would then be ingested through the nozzle and then pass through into the test section harmlessly. What actually ended up happening was it didn't rupture as literature would suggest, but broke off in large pieces, and we'll see in a little bit those large pieces ended up interacting with the test. So now I'm going to go into the results, the imaging of the shock waves, talk about the tesseration that we were able to observe, and then I'll conclude on my So this is a video that was captured at 2,500 frames per second of the test. So there's a bunch of things going on, but I'll break it down and go through in detail what each one is. So this is just to give you a good overview of what the test will look like. Let it play one more time. I think it stopped for whatever reason. But so this is these are stills on the left of a wind off image of what we were able to observe, and on the right, wind on, so in the middle of the test. So you'll notice that usually this is called a shadow graph setup, and usually with a shadow graph, these lines are much more crisp. And that would be because you have a really nicely collimated beam, and you either have mirrors or lenses which are able to properly focus the light in the way that you need. Because for a number of reasons, one of which was having lenses that weren't quite designed for what we needed them, there was a lot of distortion or aberration in the image. So you can see that there's kind of like a hard image of that wedge right here. It's just looking at the tip of the wedge, and then kind of a blurred outline of that image. And then there's a little bit of distortion where the image seems to curve down because of the shock waves coming off of the end of the nozzle, most likely, or off the end of the model. But this is the quality of imagery we were able to produce. I think in the future we can, with some more refinement of the setup and some different hardware, we can improve it a lot. But I think it's enough to validate the test. So in order to measure, because the image is distorted, it's not super clear how to measure the shock waves. But what I ended up doing was I traced out that hard outline, this dark line right here on the wind off image, and then the outside of kind of the blurred image, which I think is just kind of comes as a result of the lenses we used, and then drew the horizontal line through the center of the model, and then used that as a stencil and placed it on the wind on image and lined it up with the model here. And what I found was that the shock waves lined up almost perfectly with the lines of that blurred outline image. But then I traced out through the center of each. Oh, no.
Is that the
Sorry.
computer?
Hey Damon, can you still hear us?
I can still hear you, but the screen went away.
Screen went away.